Hello everyone, welcome back. So I will be doing the next set of 5 organic questions from the June 2020 CSIR-NET question paper. Okay. So this will be question 27 to question 31. Please understand I am doing only the organic questions. So let's start. The first question says the correct statement for the following transformation is, and you are having this molecule where you are having ketone at one end and at the other end you are having amine, right, and it reacts with another molecule of ketone, and then you are getting two products. Basically these two are condensed product. I will show you how does it form, P and Q, and it says condition A is there and condition B is there. What is condition A? Condition A is alcoholic KOH, so basic condition, and condition B is acidic condition where you are having H2SO4 and acetic acid. So it is asking under which condition which is formed, P is formed or Q is formed, and what is that, thermodynamic control or kinetic control. So option A says P is preferentially formed via condition A. So condition A, that means in aqueous condition, sorry, in basic condition, aqueous KOH and ethanol, so ethanolic KOH, that would be under thermodynamic condition, or Q is preferentially formed via condition B under thermodynamic control. So it is saying that product B is formed under basic acidic condition, condition B you know is H2SO4 and acetic acid, that would be under thermodynamic control. So what is product, which is the product? Product Q. So product Q is this more substituted alkene, and C is option C is P is preferentially formed via condition B under kinetic control, and option D is Q is preferentially formed via condition A under kinetic control. So we will understand the answer thoroughly, then we will be able to answer the question. So let us first understand what is product P and what is product Q. So this was the ketone, you saw this ketone, this was there in the question, and this was the ketone and amine. So on benzene ring you are having amine and ketone part. So it's basically two condensation reactions are occurring. So this NH2, this H2 will be lost and oxygen is lost, so that you get a double bond here, and then from the center carbon, that is CH2, not the terminal CH3 to this C double bond O, because this hydrogen on this carbon is acidic to a certain extent, and this hydrogen is also acidic to a certain extent because they both are beside carbonyl. So if you remove one of the proton, the negative charge will be stabilized. So proton can be lost from either end. So right now I am showing from the middle one it is being lost, so that you are getting more substituted alkene. So this is your product Q, right? And then product P will be when from the terminal CH3, this part I was saying. So from terminal CH3 H2 is lost and then NH2 it is lost, so you are getting less substituted alkene. I hope everybody understands what is less substituted and more substituted alkene. So if you see the alkene here, one extra methyl group is there, here hydrogen is there. Now if hydrogen is there, hydrogen is not considered as substituent, and therefore Q is considered as more substituted alkene and P is considered as less substituted alkene, right. Now let us look at condition B. So what was condition B? Condition B was sulfuric acid, acetic acid, and heat it up. So basically sulfuric acid, so when you add sulfuric acid to ketone, they undergo tautomerization. You can start seeing tautomer where you will have ketonal tautomerization and you will get more of this, not more of this, more of this product will be there, but you will see certain extent of this product form, that is enol. I should have drawn a equilibrium sign, that would have been better, yeah. So this is your enol. So this is keto, this is enol. So in enol you see you are having OH and double bond. Now of course double bond is formed towards the more substituted side rather than less substituted, because alkenes, you know, more substituted alkene is thermodynamically more stable, right. So one thing is very clear, under condition B, that is acidic condition, the reaction is under thermodynamic control. Second thing is it should give you more substituted alkene, that is product Q, right. Then this will undergo aldol condensation with the other ketone. So let us see this reaction. Basically under acidic condition this gets protonated, this ketone gets protonated, and therefore this carbon becomes highly electrophilic. Otherwise, unless you activate this carbon, it's tough because this carbon does not have that much positive polarity. Once oxygen attached to hydrogen, so though oxygen looks like it is positively charged, oxygen is pretty much neutral. Oxygen pulls away all the electron towards itself, and this carbon has a lot of positive polarity. So this will attack through this, so it is under thermodynamic control. It attacks from here, and then you get this, and then base is basically anything what will be there. Sulfuric acid, acetic acid is there, so they themselves will act as base. HSO4 is there, H2SO4 is there. So once you pick up proton, you will have HSO4 minus, that itself picks up proton. You get here, this is lost, and you are getting thermodynamically stable alkene, right? And the second is again condensation reaction. So again we will just write the mechanism. So this picks up proton, and you get electrophilic central, this amine attacks, then you get NH2 plus, this goes and attacks, this is lost, and this is lost. So this simple mechanism. And so what is very clear is under condition B, that is sulfuric acid, acetic acid, acidic condition, Q is preferentially formed, that too it is formed under thermodynamic control. But what happens in basic condition? Let us look. So you are having QH, it will pick up proton. So there are two things, it could have picked up proton from here or could have picked up proton from here, right? If it picks up proton from here, right, you get a secondary alkene. Whereas if picks up proton from here, you get a primary alkene. You know, alkene, primary alkene is definitely more stable than your secondary alkene. Oh, sorry, not alkene, anion. So what you are getting, if you pick up proton from here, you are getting a primary anion, but if you do not pick up from this proton, you got a secondary anion. Now primary anion is more stable than your secondary anion. Why? Because when you are having secondary anion, you are having, when you are having secondary carbanion, you have another substituent which will donate electron and make it more unstable. Whereas here you are not having that extra substituent, therefore primary carbanion will be there. Now this is kinetically favored because finally it undergoes this kind of reaction, okay, it forms enolate anion, but how fast it is removed is what is kinetics. So kinetics is about how fast it removes so that it gives a more stable primary carbanion, okay, and apart from that this is less hindered also. So this is definitely a kinetically favored attack from the less hindered side, and this goes and attacks you get negative charge, then this oxygen comes here, this, you know, carbon is more nucleophilic than oxygen because carbon lobes is bigger and energy is higher than oxygen, because on oxygen electrons are more happy, is more stable because oxygen is more electronegative. On carbon electrons are not happy, so they have high energy. So you know, when a reaction, HOMO of the nucleophile attacks LUMO of the electrophile. So HOMO means highest energy way. So carbon has higher energy than oxygen, so therefore carbon is more nucleophilic than your oxygen, and therefore this will go and attack here, this comes here, this picks up proton, and then this again will be lost. So this is simple reaction. So what is very clear is under option A, that is basic condition, reaction will be under kinetic control and the product you are getting is kinetically favored rather than thermodynamically. So therefore answer is option B. So let's look at the option B. So option B says Q is preferentially formed via condition B under thermodynamic control. So we saw that very clearly, Q was more saturated alkene, you can see here, and under thermodynamic control because it was under condition B, that is sulfuric acid and acetic acid. Moving on to the next question. The question says the major product formed in the following reaction is. So you are having lot of OH, basically OH is here, ketone is there, this also basically you are having ET3 and basic condition, so this also can go ketoenol tautomerization, so you have O minus, and then you are having this acetic acid, sorry carboxylic acid, so you are again having OH group and you are reacting it with trimethyl silyl chloride. You know, oxygen has great affinity for silicon, fluorine also has great affinity for silicon. So this is trimethyl silyl chloride. I hope everybody understands what is it. So you are having silicon here and you are having 3 methyl groups here, and you are having one chloride here, right? So what happens is basically silicon is highly electropositive, more electropositive than your carbon. So carbon is more electronegative than silicon, so carbon takes away electron, right? And silicon is very big also. So what happens, it gives away all the electrons, so silicon gets very concentrated positive charge. So it's all about charge interaction. Oxygen, you know, is very small, so lot of negative charge density. Silicon also has lot of positive charge in density. So it's like hard base interacting with hard acid. Okay, so silicon is very hard acid, is next to that of proton. So that's what will happen. All this OH will attack, and then we'll see what will happen in the next step. And then these are all the products we have to see. So once we know the answer, we no need to look at the options A, B, C or D. We will get the product, then we'll understand. Okay. So in the first step, they are using excess trimethylsilyl chloride. Oh, C is missing. I'll change it. Okay. So what happens? Because excess is there, this trimethylsilyl chloride will attack on all oxygen. So first this one, then this one, and triethyl, and you get silyl protection, OTMS. But just not that. Also, this proton is acidic because it is next to carbonyl group, and therefore this will pick up proton, and you are getting O silyl group here also, right? Now what happens is, now next piece is, if you remember, yeah, next you are adding this molecule. This molecule is very interesting, and then you are having BF4 minus. Now BF4 minus is basically fluoride donor. So boron is there, and you are having 4 fluorine to it, which has negative charge, right? And it cannot be negative charge unless one counter cation is there. So this is part is the counter cation, okay? And you are having 2 fluorides. So what happens is, because boron is having negative charge, all the bonds from boron are nucleophilic. So all these sigma boron fluoride bonds are nucleophilic in nature. They have negative polarity. You know, fluoride ion has a great affinity for silicon, so it will go and pick up. Now, apart from that, if you look at here on this molecule, there are 2 electrophilic center. Now this fluoride is highly electrophilic, more than even this one, right? Even this carbon, because generally carbon is a good electrophile if electronegative substituent is there, but because here fluorine is attached to nitrogen, that is positively charged. Okay, so this fluoride has good anti-bonding vacant orbital, which will act as electrophile. So let us look at the mechanism. So once this is formed, then what happens is, yeah, this fluoride goes and picks up this silicon, and this is deproduction step. This is the basic where everywhere we use this, we add fluoride ion. So this picks up proton F minus and comes here, and once you work up, it will pick up proton, it becomes OH. This also will become OH. Here what happens, rather than this goes up, and this carbon, you know, carbon is much more nucleophilic than oxygen, because carbon HOMO has higher energy than your oxygen HOMO, and therefore this goes and attacks here, and this comes here, and fluoride is picked up. This was interesting. This could have been very confusing, because it looks equally good that could have attacked carbon. So if such question comes, I would rather say just leave it off. Yeah, next is question 20, and this was simplest question. This was interesting question. So it says the guest molecule which will fit inside alpha cyclodextrine by interacting with both rim and cavity. So rim is the outside part, cavity is the whole part. So basically it says cavity means you have to first look how big is the hole. If the hole is big enough, then you need to add big molecule. Then rim you have to see what functional groups are there. So you have to find out accordingly, are interacting functional groups there or not. So first you should know what is alpha cyclodextrine. So this is alpha cyclodextrine. Basically sugars are attached to each other, glucose molecules are attached through 1,4 alpha linkage. Okay, so 1,4, basically it has lot of OH groups, very polar. So let us look what will fit in the rim. So this rim has lot of OH, so it should be able to form hydrogen bonding. So if you look here, absolutely non-polar, so A will not fit in at all. B is also highly nonpolar, no ways. C has polar OH group, D also has polar OH group, polar NH plus group. But thing is, D is highly small, okay, very small in size. This is big, tertiary butyl is big enough, so it will fit in the cavity. So answer should be option D, because big enough to fit in the cavity, and then it has functional groups which will form hydrogen bonding with the rim. Thus answer is option number C. Moving on to the next question. Question number 30, it says the major product formed in the following reaction is. So you are having this molecule, you are reacting with LDA. Now you know LDA is a very powerful base, and then you are reacting with benzyl bromide at minus 60 degrees Celsius, and then you are asking what is the product formed. So this is also pretty simple question, let us do it. So LDA is a powerful base, it will pick up proton from the alpha carbon of carbonyl. So this is the alpha carbon, because here negative charge is stabilized, delocalized with this carbonyl, and you are having this kind of species. Now the thing is, lithium is a very hard cation, so it always tries to coordinate, it forms to kind of chelate, okay, and because phenyl ring has lot of electron density, pi cloud is there basically, therefore this gives negative charge to the lithium and chelates and forms kind of bridging with O minus and lithium. So you have something like this, okay. Now please understand, this is the most stable conformer, because as soon as interaction occurs, energy is released, it is more stable. Now what happens, once you fix in, you can see this methyl is towards the viewer and hydrogen is away from the viewer. So from front, attack is blocked because methyl is more bulky than your hydrogen. So attack will happen from behind, and what will attack? Benzyl bromide, as we saw. So you are having benzyl bromide here, and therefore this O minus comes here and this goes and attacks here. As I have previously told, oxygen more than oxygen, carbon is more nucleophilic because its HOMO is higher energy. Oxygen is more stable, you understand this, oxygen is more stable. Carbon is, electrons are happy with oxygen, electrons are not happy with carbon, because oxygen is more electronegative, it stabilizes electrons. Carbon does not stabilize, therefore it has higher energy, so it is more nucleophilic. So this goes and attacks here and you get this, and then benzyl halides, you know, are excellent electrophile, because anti-bonding orbital of CX bond is very weak. I did explain, I have not explained very well, but it will be interesting to explain. Let me take this opportunity to explain this part, okay. So you are having benzyl bromide, basically this is your benzyl bromide, and you are having CH2 and you are having X, right. Now X bond is not favorable because X is always chloride or bromide or iodide, here it is bromide, bromine. So carbon bromine, there is no size matching, X is very big in size, bromine is very big in size, therefore bond is already weak and it has big anti-bonding lobe. Now because benzene is just next to it, it already pumps electrons in the anti-bonding molecular orbital. When you pump, what happens? This is already very weak. So when you donate electron in the anti-bonding molecular orbital, the bonding molecular orbital becomes very weak, and therefore lot of electron density is available, lot of vacancy is available in this anti-bonding molecular orbital, and this bond is already very weak, and therefore it is a wonderful electrophile. So this goes and attacks here, this goes, and please understand, it will attack from behind because bulkier part is front, and therefore you are having this. Thus your answer is option, what is answer? The answer is option A. So what I have said, it's written here, so you can read it probably. I will go slowly. Please pause it if I am fast. Right. The last question for this video. The question number 31. The major product formed in the following reaction is. So you are having alpha beta unsaturated ketone, you are having triphenyl phosphine and TBSO-TF. So it is tertiary butyl dimethyl silyl triplet. So triplet, you know, triplet is a wonderful leaving group, silyl group is there. So silyl will act as a wonderful electrophile, it accepts electron, right? And TBF is again tetra N butyl ammonium fluoride. So basically when you want to add fluoride F minus, you cannot add some KF or stuff like that because they will not dissolve. So you need to add organic salt. So this is the organic salt where you can add F minus, right? And first step is triphenyl phosphine TBSO-TF. Second step is N-butyl lithium, you know, is a very powerful base apart from butanol and TBF, and they are asking what is the product form. So again this was very simple reaction. So you go step by step, you will understand, it's not at all tough. So first step is attack of PPS3 alpha beta unsaturated ketone. So what happened? Phosphorus is large in size and with lone pair of electrons is large in size, and its nucleophilic attack would be orbital interaction based rather than charge based interaction. Yeah, I will come to it. Yeah, basically what happens is this phosphorus does not have concentrated negative negative polarity. Because phosphorus is very big in size, this electron pair are nucleophilic in the sense they act really as nucleophile rather than as a base. So it will go and attack the center which is more electrophilic because it's all about orbital interaction. So it's a big lobe is there, that lobe has electrons, so it has negative charge density and negative charge concentration polarity. So it will go and attack, but please understand, because it is quite stable, it is not looking for immediate positive charge, it is looking for stability. So rather than attacking here the what happens is the lobe is very small. If you look at the size of the molecular orbital, this lobe is very small because it has next to oxygen, oxygen shrinks the lobe. So here nucleophile will not attack where it is about orbital interaction. This lobe is much bigger because it attaches to another carbon, so lobe is bigger, whereas this lobe is smaller. So unless you have high negative charge density, something like if what it was F minus or something like that, okay. So when you are having huge amount of negative charge, this will go and attack here rather than going and attack here because this negative charge just wants to go and attack. F minus is not example, I can say Grignard reaction, that would be the right example. So Grignard goes for, because high amount of negative charge will just go for high amount of positive charge, that would be charge interaction, but here it is orbital interaction. So this PPS3 goes and attacks on this goes up and you get negative charge, right? And then what happens, this negative charge goes and attacks on the silyl. So you know this is the triplet part, triplet is a good leaving group. This is TBSO-TF, so tertiary butyl dimethyl silyl fluoride. So you know oxygen has great affinity for silicon because again charge interaction, lot of negative charge on oxygen, lot of positive polarity on silicon. So this goes and attacks and this leaves and you are getting this species, right? And then what happens, you are adding, next step, if you remember, you added N-butyl lithium and butanol. So once you add N-butyl lithium, it will pick up proton and you get kind of double bond here because phosphorus ylides are highly stable. Okay, it's not exactly double bond, please understand. Its more better chemical structure would be this one because phosphorus is much bigger in size than carbon. So this bond is very long. So if you think that this negative charge goes and overlaps with this, that happens very little amount. So this double bond is not there, but it's a highly stable ylide. You know, sulfur ylide and phosphorus ylide are quite famous because they form easily, and therefore it will lose proton from the next when you add N-butyl lithium, this proton is lost next to the P plus. Basically phosphorus is not happy with +3 oxygen state, it wants to become +5. So that's why all these things happen. And then once negative charge is formed, this goes and attacks butanol, and then it is simple Wittig reaction. This goes and attacks here. Basically when you see PPS3, please understand it will go out as POPVS3. Do anything so that it forms POPS3. Phosphorus is not happy as phosphorus, it always wants to become P double bond O plus 5 oxygen state, and that to great affinity for oxygen. So this you go and attack here, the negative charge comes here and then this comes here, this is simple Wittig reaction and you get the alkene. Last step you can imagine TBS has to go with this silicon and you are adding fluoride because we saw we are using what was the species, tertiary butyl ammonium fluoride. So this F minus has great affinity for silicon because silicon has huge positive polarity. Fluorine you can see very small in size and one negative charge, so huge concentrated negative charge. Again charges interaction, this goes and attacks here, this comes here, this comes here and picks up proton, and I should not written H2O plus, just from water it will take up, okay, and you get this. So that's the answer is option A, right. I'll go slowly, you can pause and read it again whatever I have written. Yeah, so is the question, these are the options. Please pause it if you feel it I am going fast. Right, the answer is option A, this was option A. That's it for today's video, thank you very much.